Not a fan of the glare. Oh, like, could I film at that one? I don't know if that'd be better. Maybe. Oh. We'll see if people complain. Howdy, Elijah. Can you guys hear me okay? Nice. Okay. Fuck. You'll be fine. It's also weird for you guys because you can't read all the chat comments. Yeah, you could. Damn it. Okay. Give me a few minutes and then we'll get started. I'm still. You guys want to go for break? Yeah. I'm still thinking about it. That is a pretty good name. No gummies today. I'm all out, unfortunately. Okay. I'm I'm also not thrilled about how the board looks. If you guys can't read anything at any point, let me know, and I don't know. We'll see what we can do. Yeah, no, I was really sad about the whiteboard situation. That's okay. We'll make do. I can deal with adversity. Okay, we can get going. So a couple 100 subscriber special. Well, I actually kind of did that during my 31B review session. I hit 100 subscribers, and so I did a Q&A. That was my 100 subscriber special. Couple preliminary comments. There's some tricky things on it, but I don't know if I'd call it super conceptual or anything like that. So if you're worried about like, oh my God, am I gonna have to prove something crazy? No. The content of the questions is at least that I've seen, it could definitely change, but what I glanced at, it is still mostly computational. So I wouldn't be too worried. Oh, okay. We can do a Q&A during this one, since it's the last hurrah for Math 32A. Damn. Okay, hopefully lag isn't too bad. Anyway, I have some juicy examples prepared for tonight, but we'll warm up with something not so juicy. Let's do, to begin, the following. Like I said, we'll experiment with this whiteboard, and if you can't read anything, just let me know. So first example is going to be, here's a function, as always. Let f of x, y be, I already forget, x squared y plus e to the yz. Try to split the board like that. I might give you a challenge question at some point. I've got plenty on my website, though, if you're looking for something hard. Okay, here's what I want to do. Nothing too crazy. I want to compute the directional derivative of f at the point 1, 2, 0 in the direction of the vector 1, 2, 2. That's part A. In part B, I'll ask, what is the maximum rate of change at this same point? So at the point 1, 2, 0. And in what direction does that occur? And then finally, I want to find a direction vector which is tangent to the graph of this function. So find a direction vector tangent to the graph of f. Sorry, what am I doing? Not the graph. I'm sorry, I'm getting confused already. Tangent to the level surface of f at the point 1, 2, 0. Okay. Sorry about that. I'm getting screwed up already. Board doesn't look too bad. Okay. F of x, y, z. Yes, thanks. I think that is why I was getting confused. This is a 3-variable function. Good call. Off to a fantastic start already. Okay, so now that I've written all this on the board and taken up like half of my board space, let's reread it to figure out what we need to do. I have a function. Part A, I want to compute a directional derivative. So then we just have to remember, how do we compute a directional derivative? Yeah, I actually didn't get enough sleep. It was a late night. Okay. There are a number of ways to think about what a directional derivative is and how to compute one, but the main computational tool for computing a directional derivative is this dot product formula. So the thing I would remember if you need to compute one of these things is that the directional derivative of f at a point P in a unit vector direction. So here u is a unit vector. You can compute this by taking the dot product of the gradient at P with u. So for part A, that's all we need to do. We'll need the gradient and we'll need a unit vector in the direction that we want to travel in. And one problem is that this says compute the directional derivative in this direction. It's probably not a unit vector. So the first step here is going to be to take this thing and turn it into a unit vector. So I would probably say let u be the direction I want to walk in. And then the question is, how do I produce a unit vector in the same direction? I just divide by its length. The magnitude of this vector is going to be the square root of 1 squared plus 2 squared plus 2 squared, which, if I can do that math correctly, 8 plus 8 plus 1 is 9. Square root of 9 is 3. Nice. Okay. There we go. There's our unit vector in the direction that we want to walk in. And then the next thing I need is I need the gradient. So next, the gradient of f as a function is the vector. The x derivative is going to be 2xy. The y derivative, let's see, from here will be x squared. And if you guys ever can't see around this setup, you can move or whatever, obviously. An x squared from here, and then when I take the y derivative of e to the yz, by the chain rule, I'll get a plus e to the yz times z. And then the last component I'll squish in over there is going to be the z derivative, which is 0 here. And then likewise, I'll get a y e to the yz. And that's the gradient as a function. The point that we actually care about, the point that we're computing this directional derivative at, is 1, 2, 0. So the gradient of f at 1, 2, 0, this will be the vector, let's see, 1 times 2 is 4. 1 plus z is 0, so this is 1. And then y is 2. Z is 0, so this is like 2 times e to the 0, which is 1, so that's 2. Okay, nice. Thanks, Mark. I appreciate it. Any reason why u has to be a unit vector? Yeah, that's a good intuitive explanation, Ricardo. The issue you could have is that if you take the dot product with like a vector which isn't a unit vector, you're introducing a scaling factor, which kind of screws up the value. And when we talk about a directional derivative, I don't want the direction I walk in to have any kind of confounding scaling factor. But yeah. Okay, we've got our gradient, got our unit vector, take the dot product, and then we'll be done. So let me see if I can squish that in down here, if you guys can see. So this directional derivative we want is the directional derivative of f at the point 1, 2, 0 in the direction u. This is going to be the gradient vector we care about, 4, 1, 2, dot the vector we found here, 1/3, 2/3, 2/3. And then I'm going to be really annoying, and I'll finish this off way down here. 4 times 1/3 is 4/3 plus 2/3 plus 4/3 is some number of thirds, 10/3. Nice. And if you can see, it looks like the directional derivative we care about is 10/3. Cool. Moving on. Anyway, basic skill that you should know how to do for tomorrow is just compute a directional derivative. That's something that I don't think we did last night, actually. Okay, so now part B, I guess I can erase this stuff. Part B says, at this point 1, 2, 0 that we care about, what is the maximum rate of change? Okay, here we just have to remember that how do I get the maximum rate of change? One way to get that is with the gradient. Oh, hey, Shai. The gradient points in the direction of maximum rate of change, and furthermore, the magnitude of the gradient, that is exactly the greatest rate of change. So the greatest or maximum rate of change which is the magnitude of 412, which is the square root of 21. Okay, so that's as fast as the function can change, starting at the point 1, 2, 0. In the direction that you walk in to achieve that is the unit vector in this direction here. So the direction which achieves this achieves, I may have spelled that right, is, you know, the unit vector in the gradient direction. So this would be like 4, 1, 2 divided by the norm of 4, 1, 2, which is 4, 1, 2 divided by, oh, I guess we found that the norm was root 21. That would do it for part B. Now, one question that you may have, maybe not, is, Joe, would I be wrong if I just said the gradient vector? Like, can I just say that this is the direction that I walk in? I would take that. I don't care. I just know that based on the homework we've had, I think in the past, Jeff has asked some questions kind of along these lines, and he's specified that he wants a unit vector every time he talks about direction. So it's not a bad idea. I think if something like this came up on the test, he would probably specify, like, please give me a unit vector. So hopefully it's clear, but to be safe, you can do it. Is it possible to compute the maximum value of the gradient? Well, you could do that if you wanted to. Like, you could take the norm of the gradient as a function, and then you could try to maximize that function, and then it turns into a 15.7 problem or whatever. Okay, so I'll put it this way. I glanced at the test. A lot of it went in one eye and out. That's not an expression. I glanced at it. I don't have all the details memorized, and like I said, it could change. But I have an idea of what's on it. No, I wouldn't worry about proofs. I wouldn't worry about anything about Kepler's laws. Yeah, don't worry about that stuff. All right, part B done. Part C says, it's going to get annoying. Okay, so part C, before I erase it, says find a direction vector tangent to the level surface of F at this point. Okay, this is maybe the first part of the question where you have to think a little bit. I have a level surface. What do we know about the gradient vector? This guy. The gradient vector is perpendicular to that level surface. So how can I find a vector tangent to the level surface? I just find any vector perpendicular to the gradient vector. And that's it. Any vector which is perpendicular to the gradient, that vector is going to be tangent to the level surface at that point. Okay, so that's all we need to do. We just need to find. So since, maybe let me write that out. Since the gradient of F is perpendicular to the level surface, that's one of the main facts about gradients that we know. We just want any vector perpendicular to the gradient. The gradient at this point is 4, 1, 2. So for example, that will dot product with the gradient to get 0, and therefore it will be perpendicular. So if it were me, I'd probably say, note that 4, 1, 2, which is the gradient vector, dot, for example, the vector 1, 0, negative 2, this is 0. Therefore, this vector is tangent to the level surface. Is that the only answer? Definitely not. There are many, many, many answers you can pick. That's one of them. So 1, 0, negative 2 is tangent to the level surface. Okay, and that'll finish our first problem off. Had a bit of a rocky start, but I'm feeling it now. Okay. Let's see. Let me catch up with questions. So, yep. How did I come up with the vector 1, 0, negative 2? I really just, so I looked at the vector 4, 1, 2, and I thought, what can I dot product with that to get 0? And then it's just a matter of eyeballing things or being creative and saying, like, well, if I just take 4 times 1, and then like minus 2 times 2, that'll get 0, and then I can just ignore the middle component. Or, for example, we could do, I don't know, 1 minus 2 minus 1. That would be another vector. So here, to get this vector, I really just kind of eyeballed a vector that would give me a dot product of 0. Okay, good question. Wouldn't the 0 vector technically be tangent to any surface? Yes. 30 seconds before, told myself that I should do, and then I didn't do that here, which is what? Oh, I raised the problem, but I wrote find a direction vector. And I literally just talked about how when you want to find a direction vector, you may as well find a unit vector. And I did not do that. So maybe what I should have done is actually divide this by its length, which would be root 5. And the 0 vector you couldn't do that with. And maybe in the question I should have asked for a non-zero vector. But yeah, that's a good point. Is there a way to find the distance between two tangent planes that are parallel to each other? Yep, you can find the distance between two planes in a couple of ways. I actually am going to do a problem sort of similar to that later, so maybe sit tight. We'll come back to that. Okay, let's move on from this one. I'll be rid of it from my life. Oh, over here. Okay, that was a non-juicy problem. Let's do a limit. We'll bump it up. Let's try this. So either evaluate or show that the following limit doesn't exist, does not exist. And the limit I want to do is the limit as x, y approaches 0, 0 of the square root of the absolute value of x times y squared over 2 times the square root of absolute x plus absolute y plus 1. Okay. Yes, I've got a couple chain rule problems planned for tonight. So we'll definitely do that. For sure. Will you get a limit that isn't approaching the origin? That could happen. And I have a problem like that planned for tonight as well. So I'm on top of it. Okay. I'll let you think for a sec. One weird thing about this whole online thing is I'm so used to like asking the big crowd for ideas and stuff, and it's a little weird doing that with like 7 people, but it's okay. If anyone has any ideas, you can let me know. And if not, think about my general flow chart for attacking a limit that I described last night and I've described earlier in the quarter, which is, well, oh, damn it. Let's do that. Sorry. Good catch. Okay, so the original limit I wrote, yes, you would just plug it in. So that was a mini example. Now I've changed it a little bit. But no, you're correct. The original limit I wrote you could just plug it in and you get 0. So maybe we're not off to a good start still. Okay. General flowchart for limits, can we plug it in? That was what I was starting to say. In the original case, yes, we could. Now we can't. So then what do I try? Typically after that, I'll try approaching along the coordinate axes, just because usually I can do that pretty quick in my head. For example, if I approach along y equals 0, excuse me, the new, something like that, that's 0. So if I approach along y equals 0, I'll get 0. Likewise, if I approach along x equals 0, I'll get 0. And so that doesn't tell me anything. It doesn't tell me that the limit is 0, because that's just 2 approaches. In order for this kind of thing to work, you would want to find multiple approaches that give you different values, but both of those gave us 0. Okay, someone has an idea. Abhishek says, what if we approach along y equals the square root of x? Okay, let's try. Now, if y is the square root of x, what does this thing become? And since I'm doing this in my head, I'll be a little imprecise about it. And then if it works, then we can write it down formally. If y is the square root of x, then the numerator becomes root absolute x times the square root of x squared is absolute x over 2 root absolute x plus the absolute value of the square root of x. And what happens there? Okay, so he meant absolute with the inside. So downstairs here, if we do that, this will be 3 root absolute x. And then on top, how many powers of absolute x do we have? We have 3 halves. And this simplifies to x to the 1. And that goes to 0. So that also didn't tell us anything because it was another approach which gave us 0. But this is the kind of maybe thing to start trying. It's the kind of thing to start thinking about. So thanks for the idea. And that was a little sloppy. If anyone's confused, you can let me know and I can run through this again. But I claim that if you approach along this path, you'll get 0. Yeah. Okay, so now Abhishek says squeeze theorem. I like that. Ricardo says squeeze theorem too. Elijah says trig sub. I don't know about that. If you mean polar coordinates, you could think about that. You could probably rig up a decent solution with polar coordinates. I think I would do the squeeze theorem. And this is hard. This kind of thing is tricky, and it's something that I don't think you see very often. But it's the kind of argument that maybe once I do it, you'll be like, oh, like, wow, that was nice. So let me write out what I would do, and then if any of you guys can come up with a different argument, go for it. But I'm going to use the squeeze theorem because I want to show that this limit exists. First of all, why would I suspect that the limit exists? Well, we checked 3 different paths and we got 0. That doesn't necessarily suggest that the limit exists, but a good kind of principle to keep in mind, and this is imprecise, this is only intuition, so don't take this to heart or anything, but what's like the total degree on top, sort of? It's like 2.5 or something like that. What's the total degree on the bottom? It's maybe like 1 at most. Again, sort of, that doesn't really make sense, but roughly in my head, the power on top is bigger in some sense, and I think that that's going to kick in and bring everything to 0. So that's the maybe extremely vague intuition that suggests that this limit might actually exist and go to 0, because the top seems stronger. Okay. So how could I formally argue for this? Like I said, this is the kind of thing that you might just have to see, and then you'll be like, oh, okay, nice. What I would say is, first of all, do you agree that this thing that we care about is always non-negative? Fair enough. Y squared is always non-negative. Absolute y is always non-negative. The square root expressions are always non-negative. So I think it's relatively straightforward to see that this expression is at least 0. Next, here's my question. 2 root x less than that plus y. Yes. Yeah. So I think Katie has the right idea, which is I'm going to write a new fraction on the board, and you guys tell me how they compare. I'll leave the top alone. And then on the bottom, I'll just write 2 root absolute x. Question, between this fraction and this fraction, which one is smaller? This one, because the denominator is for sure bigger. The denominator over here, I just added some positive stuff. So the denominator is bigger here, the numerators are the same, which means I have an inequality like this, and then things simplify, and so what we've shown is that 0 is less than the absolute value of x, y squared, blah, 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 blah. So the thing that we really actually care about, cancel out these square root of x things, and we'll get y squared over 2. And now take the limit of this thing as xy goes to 0, and by continuity, this goes to 0. So apply limits to all parts. Oh, this is a lot of writing. Okay, I applied limits to all parts. And then the point is, well, the limit, I didn't write 0 here. The limit of 0 is 0. The limit of y squared over 2 as xy goes to 0, 0 is 0. I can just plug in 0 for y. And then this thing slides right in here. And then by the squeeze theorem, what have we shown? We've shown that this limit is 0. Try.
The intuition thing you were talking about earlier, does that like become a slippery slope the closer and closer the total degree is? Like, is it less
Yeah, maybe. Kind of intuition to think about, which is like if the total degree in some sense is bigger on top, then it might go to 0. Okay. Oh, one more.
Explain why when you chose to do the first step compared to the same thing without the y.
So I chose to do this first step mostly because I could see that if I did that, I could cancel out some stuff and get something that would simplify luck and a little bit of just identifying that if I did that, then things could simplify. So the limit, let me finish this off and then I'll look at the chat questions of blah, 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 blah that we started with is successfully 0. Okay. Yes, I will do my best to repeat questions in the room. So why not just compare to square root of x y squared Yeah, I think Aman's got the right idea, which is if you were to compare with, so if I wrote down blah, 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 so that's a good question. We can think about that. If I wrote down this, is that true? Aman's correct, which is that it's not true because if x and y are very small, like very close to 0, how do these two numbers compare? Well, the tops are the same, so I just have to compare the denominators. And if x and y are small, this denominator is way smaller than 1, which means that this fraction is actually way bigger. So this comparison is actually not a correct comparison. Nice. Okay, tricky, tricky, tricky. Other questions about this one? So for sufficiently large x we're sending x and y to 0, so I don't really care about x and y getting big. Try. Yeah, it's okay.
Like, so you thought like the power of 1 is bigger and 1 is 0, so we think the limit exists and it's probably 0. What would tell you that the limit doesn't exist?
So the question was, earlier I was explaining some vague intuition that if the total power on top was bigger than the total power on bottom, then it might go to 0. What kind of thing would suggest that the limit doesn't exist? A lot of time, and again, it doesn't work this way in general, but a lot of times if the total powers are the same in some sense, things might not go to infinity or something like that, not exist. Again, it doesn't always work that way. It's just kind of a rough heuristic. Yeah, I guess so. You could either say infinity or not exist. Yeah. Will there be limits as x and y go to infinity? Probably not. That's a little difficult to make sense of in the multivariable setting, so probably not. You'll almost certainly only get limits that approach some point in the plane and probably, or in 3 space, probably the origin. So, okay. That was juicy to me. Let's move on. Do you want to do juicy again or not juicy next? Juicy again, okay. I keep looking at the wrong page. Okay, we'll do juicy again, but I'll spread the juice out throughout. So this one's good. Let's do this next. For those of you worried about conceptual stuff, this is maybe what I would consider like a conceptual type question. If I were writing a test, I would probably put something like this on, so you can interpret that how you may if I were a professor. Okay, so this will be a long one to write out, I think, so bear with me. Let x of t and y of t be functions with the following graph, with the following graphs. So tx, let's do there's x of t, and here's y of t. So t, y. And then I have a handful of things that I want to ask about this. Oh, maybe, and then I'll say next, let curly C be the curve with parametric equations given by x and y. With parametric equations given by x equals whatever x is and y equals whatever y is. Okay, so here's what I want to ask. Is there a point on curly C with vertical tangent line? That's one thing I want to ask. What else? What about horizontal tangent line? So same question for horizontal tangent line. Then, is this curve, is it given by the graph of a function? So is C the graph of a function? Maybe let me say a function of x. And then I think I had one more question. Oh yeah. That I'll squeeze down here. You can yell at me in the chat if you can't see. Next, let f of xy be. Actually, I'm going to write this up here. Sorry. Okay, so part D, let f of xy be x squared minus 2y. And then let g of t be f of x of t comma y of t. And my question is what? Is g prime of 0 positive, negative, or 0? Okay, that was a lot. So let me reread this now that I've put all of it up there, and then we'll start thinking about things. So I'm giving you the graphs of two functions of t, x of t and y of t. And then c is the curve, which is the parametric curve, given by these two functions. And then I want to know some stuff. So let's think about part A. The question is there a point on the curve with vertical tangent line? And I'll try to not be in the way. Oh, I have more juicy problems. I'll spread them out though. Okay. Katie, tell your mom that I'm glad that she likes that I call math problems juicy. Okay, so Aman's got the right idea, which is, what would it mean for this parametric curve to have a vertical tangent line? There's a couple ways to think about it. Maybe here's kind of a direct way. Recall, how could you compute the slope of a parametric curve? The slope of a curve, as you know, as we know it from single variable calculus, is dy dx. So the slope at any point of this parametric curve, which by that we mean dy dx, in parametric language, how can we compute this? This is like y prime of t over x prime of t. So to have a vertical tangent line would mean that the slope is like infinity, which means I want it to be something like a number divided a vertical tangent line. So what I'm looking for is I'm looking for a point where x prime is 0. So then I go over to the graph here. X prime, that's just the normal derivative, the normal one variable derivative. It looks like it's 0 when t is 0. Furthermore, that's not enough. To have a vertical tangent line, we also need y prime of t to be non-zero. But that's also the case at the point where x prime of t is 0, which it looks like is t equals 0. Uh-oh. My roommate just texted me and said LA is going on lockdown, I think. I don't know. Effective at midnight? Okay. Okay. So maybe not lockdown. Yeah. What was I talking about? Oh yeah, so at t equals 0, x prime is 0. Also at t equals 0, y prime, the slope of y, is definitively not 0. It looks positive. So that checks out. That looks like a vertical tangent line. Yeah, so a lot of you guys are right. Okay, we'll focus on the math for now. Like I said, the only subtlety is that to find a vertical tangent line, x prime needs to be 0, but very specifically, y prime should be non-zero as well. So let me write that down. But I would say that yes, there is a vertical tangent line. So my answer would be yes, there is a vertical tangent line. That says tangent. At the point we decided that, or I decided that it happened at t equals 0. So the spatial point would be x of 0, y of 0, whatever that is. And the reasoning is because x prime of t is 0 and y prime of t is not 0. Okay, so yes, there is a vertical tangent line. What about a horizontal tangent line? I think Amand had the correct idea in the chat as well, which is the flip-flop of this. A horizontal tangent line is going to occur when y prime is 0, because I want the slope to be non-zero, to be 0. I want the slope to be 0, so I need y prime to be 0. It looks like that doesn't happen. So I would say no, that there are no horizontal tangent lines. Nope. Y prime of t, according to my beautiful picture, is never 0. Okay. C, is curly C the graph of a function f of x? Okay, so Ma asks, can we actually conclude this if I'm not showing the whole graph of like x of t and y of t? I think usually when you're given a picture like this, you kind of just have to only look at the information you're given, and you kind of have to assume that maybe this is a curved segment or something like this, and I stop here. Okay. So any ideas about this whole function thing? Shai?
I think no, because like if you imagine, like I just kind of imagine like the x graph moving along the x-axis and y dotting above it, and it hits the same x value twice, different lines.
Okay, Shai's got the right idea, which is, yeah, and so Anna has the right idea too, which is that first of all, what would it mean to not be a function? How do we show that something is not a function? We show that it fails the vertical line test, which is just to say that on this curve, there's a point with the same x value, but different y values. And that definitely happens here. For example, there are two different times that give different y values. So this time and this time, what happens on the curve is that you have a point with x coordinate 0, but two different y values. That means the vertical line test fails, and therefore, you guys are correct. This is not a function of x. So let me write that down, and then I'll look at the chat questions again. Nope. So the curve C fails the vertical line test because there are points, specifically of the form 0, comma, y1 and 0, comma, y2, where y1 and y2 are different. So nope, it is not a function. Nice. Let's see. So the answer to part C is no. It is not a function. The good question is it a function of y? So we could ask, does it pass the horizontal line test? In other words, is there a point, what would that mean, with different x values corresponding to the same y value? That does not happen roughly because all of the y values are distinct here, right? Of y, and I think in this case you probably could. Okay, that was part C. I forget what part D was. Oh yeah, this thing here. Let me, hopefully this isn't too confusing with the board work. Let me erase this stuff. I'll keep the pictures up. And we'll do part D here. Okay, so what in the world is happening? We're defining a function on the xy plane. Yeah, oh God, the chain rule, that's correct. So this part D is a chain rule problem. In total on t, but it does so by way of x and y. So we care about g prime of t. In the tree picture here is that g depends on x and y via f, but x and y both depend on t. So to compute g prime of t, there are two avenues by which that could happen. G prime of t is going to be, how does g change with respect to x? Well, that would be the partial of f with respect to x. So this would be like f sub x and then times the change in x with respect to t. So times x prime of t. Plus, likewise, we've got this leg of change. G could also change with respect to y, which would be f sub y times y prime of t. Okay. So the thing that we care about is g prime of 0. So the x prime of 0 plus f sub y at the point x of 0, y of 0 times y prime of 0. Okay. What is x prime of 0? It's 0. So that term actually goes away. So I'll continue from over there. I get a big 0 plus the y derivative of f is just negative 2. And then times y prime of 0. Now, we don't know what y prime of 0 is, but if I look at the picture here, it's positive. So y prime of 0 is definitely a positive number. So the derivative g prime of 0 that I care about is negative 2 times a positive number. Excuse me. So g prime of 0 is negative. Okay. Done. Questions. Why do we care about g prime of 0? I have no clue. The lag is making Elijah sad. Yeah, we care about g prime of 0 because I wrote the question to compute g prime of 0. That's all. Okay. So there's kind of a lot going on here. Any questions from you guys or from you guys? We can move on to something not as juicy next. Cool. Anyway, maybe main takeaway of part D is just this picture. That's the chain rule. If you can get this kind of stuff down, I think you'll be fine. Oh, okay, I know what I want to do next. I don't know if this is juicy or not, maybe. Let's see, what do I want to erase? I'll erase this. Now, earlier, one of the Amans asked about finding the distance between two planes. This will be kind of similar to that. Let's see, how many people are actually here? 7, big crowd. Any reason how I got the formula for the chain rule? I don't know if I understand the question. If the question is where does something like this come from, to me it comes from this picture, which is just that if I want to track how g changes with respect to t, there are multiple levels here. G depends on x and y both depend on t. So when you change t a little bit, x could change, and I get change that way, but also y could change, and I get change that way. And when you do this derivative chain rule stuff, you have to account for both. So this chunk right here is this change, and this chunk right here is this change. But I don't think I don't know if I understood the question. Okay. Oh, right. This is what I was going to do. So next I want to find the point on the plane x plus 2y minus z, 1, 2, 3. And had g of t just been x of t, y of t, wouldn't g prime of t just be, yes, that's correct. Okay, that's the cool part about this. So we'll do at least 2 different solutions. Okay. So I'll let the world think for a second while I text my roommate OMG. Any ideas? Okay, so okay, so I've got two ideas in the chat. Chai, idea?
I was thinking you could write the distance from the, you can just minimize it. I guess like straight.
Yeah, exactly. So there's a couple things that we could do. One of them is a geometric argument, which I don't know which one I want to do first, but Abhishek in the chat suggested thinking about, so let me draw a picture here to give us some context. Here's my heuristic picture for what's happening. Here's the plane, which is a line in my picture. And here's the point 1, 2, 3. The thing that we're trying to find is the point on the plane which is closest to this given point. So that would be, in my picture, that would be like right there. That's the thing that we're looking for. One of the suggestions that have been given by a couple people are we could come up with a distance function from points on this plane to this point, and then I could treat this as a minimization problem. In other words, I could minimize that distance or distance squared function to find where that minimum occurs and get a point that way. So that'll be one of my solutions. And then the other solution is to do this more geometrically by saying that we know that the picture wasn't the best, that the angle of attack from this point to the plane that we want to travel in is given by the normal vector of the plane. So what we could do is we could parameterize a line through the point with normal vector given by the plane and figure out where that hits the plane and get the point that way. So there's two kind of completely different solutions to achieve what we want. All right, so let's do both. Let me do the geometric way first. So solution 1, and then we'll minimize a distance function afterwards. So solution number 1 is going to be based on this picture. And what I would first observe is that a normal vector to the plane is 1, 2, -1. So what's the point? Like I said, what I want to do with that is I want to parameterize this blue dotted line, which is going to be the line through the point we care about with direction vector given by the normal vector. So consider the line r of t given by, how do I parameterize such a line? I have a point and a direction vector. And to parameterize a line, I do p plus t times that direction vector. So I've got my point 1, 2, 3 plus t times this direction vector that I found, 1, 2, -1. And from vague geometric reasoning, we know that the closest point on the plane is going to lie on that line. That's the idea. So I would say that the closest point on the plane is on this line. So all we have to do is just figure out where this line intersects this plane, and that will produce the point. So we'll determine the intersection point of the line r of t, which maybe I'll simplify up here into components. This is like 1 plus t, 2 plus 2t, and 3 minus t. So I want to find where this line intersects the plane. Determine intersection points of the line and of the plane x plus 2y minus z. Okay. How do I find where a line or any parametric curve in general intersects a surface? I just plug in the components of my curve into this equation and solve for t. Okay, closest point on the plane, always perpendicular. Yes, that is correct. Yep, okay. So let's do that. So I want to find where this hits this plane, so I'll look at x, which is 1 plus t, plus 2 times y, 2 plus 2t, minus z is minus quantity 3 minus t equals 0. Now I've just got an equation that we can solve, equals 1. Now we have an equation we can solve for t. Okay, so let me try to do that without screwing up, and I probably will, so you guys will have to catch me. What's the constant term over here? 1 plus 4 is 5, minus 3 is 2. What is the t term? T plus 4t is 5t, plus t is 6t, equals 1. So therefore, it looks like 6t is negative 1, so t is negative 1/6. Now, that's not the answer. The thing that we're trying to find is the point on the plane. So my final answer needs to be an xyz spatial point, but this is the time on this line at which it occurs. So I can get that spatial point by just plugging this time. Oh no, okay, 1 minus a sixth is 5/6. 2 plus 2 times negative 1/6 is 2 minus a third, which is 5/3, maybe. And then 3 plus a sixth is 21, 19? 19/6. Okay, thanks. Whew. Okay. And that is the point on that plane which is closest to the point 1, 2, 3. Geometric solution done. That's pretty slick. Okay. Any questions about that before I do the other solution? What equation did I plug the t into? Oh, so to get the final point, I plugged this t value into this expression right here, because this parametric or parameterization represents the blue line. So this is telling me that when time is like negative 1/6, I'm right there. So I plugged it into r of t. How do you find the minimum distance? Well, now that we have the point, that would be the minimum distance. Okay, cool. So that was one solution. Geometric solution using the fact that the direction I want to travel in to get to the plane as fast as possible is the normal direction. The other thing that we can do is we can treat this like a minimization problem. Treat this like a function minimization problem. So let's do that. Let's see. I will erase this. So now we'll get some more practice with minimization. So solution 2 is, first of all, I can write down a function which computes the distance from any point in the world to this point 1, 2, 3. Okay, so didn't hear me. I don't know if that was referring to the question about how do you find the distance. What I would do is I would take the point I care about and then the point that we just found and make a vector connecting them and then take the length of that vector. That would be the minimum distance. Or you could do pretty much what we're about to do, which would be like taking the derivative of some kind of distance function. Yeah. Okay, so let's do that. Now, we have to be a little careful. The first thing I would do is I would write down a function of 3 variables which describes the distance from any point ever to this point. What would that be? That would be the distance formula. That would just be take the difference between the x values, the difference between the y values, and the difference between the z values, and square them. And then, strictly speaking, the distance would be the square root of that. But I think Katie suggested earlier that that is kind of annoying, so it might be easier to minimize the distance squared, which is equivalent. So this expression right here, this represents the distance squared from any point ever to the point 1, 2, 3. Now, oh, damn it. Okay, this happened the other night. It says I'm unable to connect to chat. Okay, so if you're watching right now, my chat just broke. I'm going to end this stream and start a new one on the channel. Sorry, I don't know how else to fix this. So I'll repeat that. Hopefully you can hear me at least. I'm going to end this stream, start a new one. We will reconvene in like 30 seconds. Okay, down we go.